Hi guys, this is the EdExcel AS Level Further Maths Paper 2 covering the Further Mechanics 1 option, and it's from the October 2020 papers. Question number 1. Two particles P and Q have masses m and 4m respectively. The particles are at rest on a smooth horizontal plane. Particle P is given a horizontal impulse of magnitude I in the direction PQ. Particle P then collides directly with Q. Immediately after this collision, P is at rest and Q has speed W. The coefficient of restitution between the particles is E. For part A, we have to find I in terms of M and W. Well, for part A, I think it will be a good idea to draw a diagram to illustrate this situation. So we've got P with mass m, Q with mass 4m, and we've got the situation before and the situation after, which we need to consider. Now, what's happening over here is the particles both start at rest, and then P is given a horizontal impulse. So let's show this horizontal impulse here. And this impulse has magnitude I. And once it's given this impulse, it collides with Q. Now, after the collision, we know that P is at rest, so we can show that on our diagram. We've got here 0 meters per second, and Q has speed W. So here we've got W meters per second. Now, if we consider the situation before, well, we know that Q is at rest initially. So here we've got 0 meters per second. And what we need to do is find out what the initial speed of P is after it receives the impulse. And this is the tricky part of the question. And the way to think about this is we need to use the impulse momentum principle. We know that impulse is equal to the change in momentum, and the change in momentum is equal to the mass times by the change in velocity. So we have over here I, that's the impulse. This is equal to m, the mass of P, multiplied by the change in velocity. Well, to ensure that we have the left hand side being equivalent to the right hand side, we have here I over m minus 0. Here you can see the m multiplies with the I over m to give I, as we see here. So therefore, if we consider the situation before, P moves off with I over m meters per second. Now we have to find I in terms of m and w. So to do this, What we can do is use the conservation of linear momentum. So we will use the conservation of linear momentum. So if we consider what's going on with particle P, we've got the mass m multiplied by I over m, and if we consider particle Q, we've got the mass 4m multiplied by 0, and this is equal to the mass of P, m, multiplied by 0, plus mass of Q, 4m, multiplied by W. So therefore what you can see here is I, and that's because we've got m times by I over m. This is equal to 4mW. So that's how we do part A of the question. For part B of the question, we have to show that E is equal to 1/4. Well, over here, if we know what I is, that's 4mW, we can use this to find out what the speed before is. And the reason that's important is because to do part B of the question, we need to use Newton's law of restitution. So for part B, we need to use Newton's law of restitution. Of course, E is equal to the speed of separation over the speed of approach. So let's adjust our diagram. You can see here, I over m, we will have 4mW divided by m, which turns out to be 4W. So the speed before is 4W meters per second. So therefore the speed of separation, you can see that's W take away 0, which is just W. And the speed of approach, that will be 4W. So E is equal to 1/4. Okay? Now for part C of the question, we have to find in terms of M and W the total kinetic energy lost in the collision between P and Q. Well, what we need to do for part C is consider the kinetic energy before the collision, the kinetic energy after the collision, and from that we can find the kinetic energy lost. So the kinetic energy before the collision, that's equal to 1/2 multiplied by the mass of P, which is m, multiplied by its speed, 4W squared. So here we've got 1/2 multiplied by m multiplied by 4W squared. So it turns out over here we get 8mW squared joules. Now of course over here the kinetic energy before for Q will be 0, because we've got 0 meters per second here. And we can find the kinetic energy after. The kinetic energy after the collision, we have 1/2 multiplied by the mass of Q, which is 4m, multiplied by W squared. So it turns out over here we get 2m W squared joules, and therefore the kinetic energy lost, that's equal to 8m W squared minus the 2m W squared. It turns out over here the kinetic energy lost is equal to 6m W squared. Question number 2. A car of mass 1000 kilograms moves along a straight horizontal road. In all circumstances, when the speed of the car is v meters per second, the resistance to the motion of the car is modelled as a force of magnitude cv squared newtons, where c is a constant. The maximum power that can be developed by the engine of the car is 50 kilowatts. At the instant when the speed of the car is 72 kilometers per hour and the engine is working at its maximum power, the acceleration of the car is 2.25 meters per second squared. For part A, we have to convert 72 kilometers per hour into meters per second. So for part A, we begin with the 72 kilometers per hour. We wish to convert this to meters per second. First thing we can do is multiply by 1000. This will convert the kilometers to meters, and then we divide this by 3600, which will ensure we get the hours converted to the seconds. So it turns out over here we get 20 meters per second. Now on our calculator we can quite easily do this. If we type in 72, and then you'll notice above the 8 key we've got the conversion options. So we press Shift 8 to access those. Scroll down to velocity, press number 1 because we're converting kilometers per hour to meters per second, and it turns out here we get 20 meters per second. For part B of the question, we have to find the acceleration of the car at the instant when the speed of the car is 144 kilometers per hour and the engine is working at its maximum power. Well, to do this, I think it will be a good idea to first of all convert the 144 kilometers per hour into meters per second. So 144 kilometers per hour, using the same idea which we discussed here, we have 144 multiplied by 1000 over 3600, and it turns out here we get 40 meters per second. What we will now do is draw a diagram to help model the situation. So we've got our car over here. We've got the mass of the car, 1000 kilograms. We've got the driving force, F, and then we've got the resistance, which will be CV squared. Now, we know over here that power is equal to force multiplied by the velocity. So with this, we've got the power, which we were told is 50 kilowatts, and of course this is the maximum power. So we've got 50,000 watts. This is equal to the velocity at 72 kilometers per hour, which is 20 meters per second. And then we multiply this by F, and therefore you can see here F is equal to 2500 newtons. And now we can use Newton's second law, which states that the sum of the forces is equal to the mass times by the acceleration. So we've got F minus CV squared. This is equal to M times by A. Now, of course, over here we know from the question that at the instant when the speed of the car is 72 kilometers per hour and the engine is working at this 50 kilowatts, we know that the acceleration is 2.25 meters per second squared. So substituting all our known values in, we've got 2500 minus C times by 20 squared. This is equal to 1000 multiplied by 2.25. So we've got 2500 minus 400C equals 2250. So we have 400C equals 250, and therefore C is equal to 5/8. Now what we need to do in this question is find out the acceleration when the speed is 144 kilometers per hour and the engine is working at its maximum power. Well, what we can do over here is find our new force, and from that find out the acceleration using Newton's second law. So again, if we use P equals F times by V, we've got 50,000 equals 40 times by F. So therefore, F is equal to 1250. So now we need to use Newton's second law, which states that the sum of the forces is equal to the mass times by the acceleration. So we've got over here the 1250 minus the CV squared. So we know that C is equal to 5 over 8. And then we multiply this by V squared. V over here is 40 meters per second. So we've got 40 squared. This is equal to 1000 multiplied by A. And we need to find out what A is. Well, on our calculator, we've got 1250 minus 5 over 8 multiplied by 40 squared. Here we get 250. So we've got 250 equals 1000 A. So therefore, A is equal to 0.25 meters per second squared. For part C of the question, the maximum speed of the car when the engine is working at its maximum power is v kilometers per hour, and for part C, we have to find to the nearest whole number the value of v. Well, as we did previously, we need to convert the kilometers per hour to meters per second. So, for part C, we've got v kilometers per hour, and to convert this to meters per second, of course we need to multiply by 1000 and then divide by 3600. So we've got v times by 1000, that's 1000 v, and then we divide this by 3600. So if we simplify all this, we get 5v over 18 meters per second. Now we have to find out what v is at the maximum speed. Now if we consider what we did previously, what we can first of all do is use this idea over here to help us find the driving force, and then we can use this idea to help us find out what v is. So we've got over here P equals F times by V. So we've got 50,000 equals F multiplied by 5V over 18. So with this we can find out what F is. So therefore F is equal to 50,000 over 5V over 18. So if we tidy this up, we have 50,000 divided by 5 over 18, which is 180,000 over V. So here we've got 180,000 divided by V. Now, if we think about what we were told in the question, we're considering what's going on when we're at max speed. And that implies that the acceleration is equal to 0. So maximum speed implies that a is equal to 0. So therefore, if we use the sum of the forces equals mass times by acceleration, we've got the forward force, which is 180,000 over v, minus c times by v squared. So here we're going to have c, which is 5 over 8. And then we multiply this by the 5v over the 18 squared. This is equal to 1000 multiplied by 0. So if we tidy all of this up, we've got 180,000 divided by v. This is equal to, if we take this over to the other side, well, here we've got 5 over 18 squared times by 5 over 8, which is 125, then we've got the v squared, over 2592. So now we need to rearrange for v. Well, you can see here that v cubed will equal, if I times through by the v, we get the v squared times v, which is v cubed, and then here we've got 180,000 divided by this. So v cubed is equal to 3732480. So therefore we can find out what v is by cube rooting. So we will raise this to the power of 1/3. So it turns out to the nearest whole number, v is equal to 155, and this is to the nearest whole number. Question number 3. 3 particles A, B and C are at rest on a smooth horizontal plane. The particles lie along a straight line with B being in between A and C. Particle B has mass 4m and the particle C has mass km, where k is a positive constant. Particle B is projected with speed u along the plane towards C and they collide directly. The coefficient of restitution between B and C is 1/4. And for part A, we have to find the range of values of k for which there will be no further collisions. Well, I think it will be a good idea to sketch the particles showing their speeds before and after the collisions. So here we've got A. We don't know much about A other than the fact that it starts at rest. We've got B. This has mass 4m, and we've got C, which has mass km. And we also know that u is the speed at which B is projected along the plane towards C. So here we've got U, and we know that C starts at rest. So here we've got 0, and here we've got 0. Now, after the collision, don't know anything about A, but speed of B, that will be VB, say, and speed of C, that will be VC, say. Now, what we need to do is find the range of values of K for which there would be no further collisions. So, what's typical with these sorts of questions is to use both the conservation of linear momentum and Newton's law of restitution. So if we use the conservation of linear momentum, now here we're only considering B and C. A isn't really involved in the collisions between B and C. So we've got 4m, the mass of B, times by U, speed of B before, plus km, that's the mass of C, multiplied by 0. This is equal to 4m times by VB plus km multiplied by VC. So we have over here 4mu equals 4m VB plus km VC. The m's cancel, and therefore we're left with 4u equals 4VB plus k VC. We'll call this equation 1. And now if we use Newton's law of restitution, we know that E is equal to the speed of separation over the speed of approach. So the speed of separation, that will be VC minus VB. So we've got VC minus VB over the speed of approach, which if we go back to the diagram, clearly that's just U. And we were told in the question that the coefficient of restitution between B and C is 1/4. So this is equal to 1/4. So if we tidy this up, we've got VC minus VB equals 1/4 U. In other words, U over 4. So if I call this 2, the idea is over here, we can solve equation 1 and 2 simultaneously to find out what VC and what VB are. Well, let's multiply equation 2 by 4, and in doing so, that will help eliminate VB. So, if we multiply 2 by 4, we've got 4 VC minus 4 VB equals U. Let's call this equation 3. And now, if we add together equation 1 and equation 3, let's write this down. If we add equation 1 and equation 3, we have 4u plus u, that's 5u. And then we've got kvc plus 4vc. So we've got kvc plus 4vc. We've got 4vb minus 4vb, those will cancel out. So we're left with this equation here. So if we tidy all of this up, we can factorize out a vc on the right hand side. So we've got 5u equals vc multiplied by k plus 4. And now if we divide through by k plus 4, we can see then vc is equal to 5u over k plus 4. We'll call this equation 4. And now what we can do is use equation 2 to help us find out what VB is. So from equation 2, we can rearrange to say that VB is equal to VC minus U over 4. We'll call this equation 5. And now what we will do is substitute in equation 4 into equation 5. So we will now substitute in equation 4 into equation 5. So we've got VB equals VC, which is 5U over K plus 4 minus U over 4. So now we can tidy all of this up. So if we cross multiply, we've got 4 lots of 5u minus u lots of k plus 4 divided by 4 lots of k plus 4. So here we've got 20u minus u times by k minus 4u. On the bottom, we've got 4 lots of k plus 4. So here 20u minus 4u, that's 16u. Then we subtract off u lots of k. And on the bottom, we've got 4 lots of k plus 4. So therefore, if we factorize out a u on the top, we can conclude that VB, that's equal to u lots of 16 minus k over 4 lots of k plus 4. We'll call this equation number 6. Now if we go back to the question, what we have to do in this question is find the range of values of k for which there would be no further collisions. Well, if we compare equation 5 with, if we compare equation 4 with equation 6, we've got over here a 5u over k plus 4. And here we've got a u lots of 16 minus k over 4 lots of k plus 4. In other words, if we compare equation 4 with equation 6, that tells us that C moves off with a greater speed than B, and B is still moving towards the right, but there'll be no further collisions. So therefore, VB, that's going to be greater or equal to 0. It could equal 0 because it could just come to rest completely. So, in other words, we've got U lots of 16 minus K over 4 lots of K plus 4. This is greater or equal to 0. And therefore, if we solve for K, K will be less than or equal to 16, and therefore the complete range of values, as we know that from the question K is a positive constant, we can therefore conclude we've got 0, which is less than K, which is less than or equal to 16. For part B of the question, the magnitude of the impulse on B in the collision between B and C is 3 mu, and with this we have to find out the value of K. So if we show this on a diagram, we've got over here impulse on B, this is I, and of course this will be equal and opposite to the impulse on C, which will also be I. And with this, we can use the impulse momentum principle to find out what K is, if we consider what's going on with C. So, the impulse on C by B is I equals 3 mu. So therefore, we've got 3 mu equals mass of C, which is Km, multiplied by change in velocity Vc minus 0. So we already know what Vc is, we were told in the question. As we previously worked out, that's 5u over K plus 4. So we have 3 mu equals Km multiplied by 5u over K plus 4. And we need to find out what K is. Well, the m's cancel on both sides, so do the u's. So we're left with 3 equals 5k over K plus 4. So we've got 3 lots of K plus 4 equals 5k. Expanding on the left hand side, we've got 3k plus 12 equals 5k. 2k, that's equal to 12, and therefore k is equal to 6. Question number 4. A small ball of mass m is thrown vertically upwards with speed square root 8 gh from a point O on a smooth horizontal floor. The ball moves towards a smooth horizontal ceiling that is a vertical distance h above O. The coefficient of restitution between the ball and the ceiling is a half. In a model of the motion of the ball, it is assumed that the ball, as it moves up or down, is subject to air resistance of constant magnitude 1/2 mg, and using this model, for part A, we have to use the work energy principle to find, in terms of g and h, the speed of the ball immediately before it strikes the ceiling. Now, as always, I think it will be a good idea if we draw a diagram to help visualize what's going on. So we've got our floor O, we've got our ceiling C, and the distance between the floor and the ceiling, we were told that's h. And we've got the particle, we'll show the particle over here somewhere. This is projected towards the ceiling with speed 8gh square rooted. And what we need to do in this question is find out the speed of the ball immediately before it strikes the ceiling. So in other words, we need to find out the speed over here. We'll call it v. And we need to use, as told in the question, the work energy principle. So if we use the work energy principle, we need to think about what we've got initially and what we've got at the end. Well, we have initially at this point O, which is our zero level, the initial kinetic energy. So let's write this down. We have here initial kinetic energy, and at the end we have the final kinetic energy. We've also got the final GPE because we are elevated above the zero level, so we add on the final GPE, and then we also have to consider the work done against the resistances. So for the initial kinetic energy, we've got 1/2 multiplied by the mass, which is m, multiplied by the speed squared. So we've got 8gh square rooted squared. This is equal to the final kinetic energy. So here we've got 1/2 m v squared plus the final GPE. So we've got the mass times by the gravity times by the height h, and then we add on the work done against resistances. Now we know that the resistive force is 1/2 mg, and therefore the work done, that's given by the force times by the distance. So therefore we've got 1/2 times by mg times by h. And what we need to do over here is find out what v is. So first thing we can do is cancel the m's out, and if we tidy what we have on the left hand side, we have 1/2 multiplied by 8gh, because we've got square root 8gh squared, and this is equal to 1/2 v squared plus gh plus 1/2 gh. So if we tidy all of this up even further, well, what we can do is subtract this result from the right hand side. So we've got 1 plus 1/2, that's 3/2, and on the left hand side we've got 1/2 times by 8, that's 4. So with a slight bit of rearranging and also multiplying through by the 2, we end up with v squared equals 5gh, and therefore v is equal to 5gh square rooted. For part B of the question, we have to find in terms of g and h the speed of the ball immediately before it strikes the floor or for the first time. So, the way to approach this question is to add on our speeds on this diagram here. We've got the rebound speed over here. We'll call this x. And we've also got the speed over here, which is what we're finding. We'll call it y. And to find out what x is, we can use Newton's law of restitution, and that's because we know that the coefficient of restitution between the ball and the ceiling is 1/2. We have over here, of course, from Newton's law of restitution, E is equal to the speed of rebound over the speed of approach. So if we go back to the question and our diagram, we know that E is equal to 1/2. So let's add this in. We've got here 1/2. And this is equal to the speed of rebound, which is what we're finding, that's x, over the speed of approach. It's approaching the ceiling with speed v. V we found to be square root 5gh. So here we've got 5gh square rooted. And if we find out what x is equal to 1/2 times by 5gh square rooted. Now, to find out the final speed over here, we can consider the work energy principle. Through the work energy principle, we've got the initial kinetic energy that's at the ceiling plus the initial gravitational potential energy. So this is at this point C over here. And at the end, we've got kinetic energy as well. So we've got the final kinetic energy. And then we've also got work done to overcome the resistances. So we will add on the work done against resistances. So for the initial kinetic energy, we've got 1/2 multiplied by the mass, m, multiplied by the speed squared. So here we've got x squared. In other words, we've got 1/2 times by 5gh square rooted squared plus mgh. This is equal to 1/2 m times by y squared plus, well, the resistive force is equal to 1/2 mg. We multiply that by the distance it's travelling, so we've got 1/2 mgh. Well, the m's cancel out and we need to find out what y is. So here we've got 1/2 multiplied by 1/4 times by 5gh. So here we've got 5/4 gh, and then we add on gh. This is equal to 1/2 y squared plus 1/2 gh. So if we rearrange, multiply by through as well, what you can see here is y squared, that's equal to 9gh over 4. So from this we can square root, and what we'll do actually is write this as 9 over 4 GH. So therefore y is equal to the square root of this, which is equal to 3 over 2 times by square root GH. For part C of the question, in a simplified model of the motion of the ball, it is assumed that the ball, as it moves up or down, is subject to no air resistance. Using this simplified model, we have to explain, without any detailed calculation, why the speed of the ball immediately before it strikes the floor at O for the first time would still be less than square root 8GH. In other words, what it's saying over here is, why is this final speed less than this speed over here? Well, to do this, we can use Newton's law of restitution. You'd find over here, if we use Newton's law of restitution, the speed of rebound is equal to E multiplied by the speed of approach. Now, because over here E is less than 1, the speed of rebound will be less than the speed of approach. And that's what we see over here. Now, if we go back to our diagram, what we're saying by that then is x will be less than v. Okay, so therefore x, which is the speed of rebound, will be less than v. And what we're saying as a result of that is there's kinetic energy lost when the ball hits the ceiling. And therefore, because of that, the speed will still be less than square root 8GH. So kinetic energy is lost when the ball hits the ceiling, and therefore y will be less than 8GH square rooted.